Hey guys, so as we're going to dive into one of my favorite parts of the year for AP Chemistry, and that's equilibrium, we need to talk a little bit about what equilibrium is, because it's one of those words that we hear a lot in non-science terminology, and it means different things in that arena perhaps than it might mean for us in chemistry. So we want to be real clear on what we mean by equilibrium. So we're going to start off by, as most things in chemistry, we're going to start off by looking at a reaction. Now, if you remember back in Chem 1, depending on who your chem teacher was, they probably told you that one of the ways that you could tell a chemical change from a physical change is the chemical change weren't reversible. And what I'm here to tell you today is that that is essentially a lie. So if we had a normal chemical reaction like our nitrogen plus hydrogen yields our ammonia, the way that we've learned that in Chem 1 and really in most of our science classes up till now is that these two things are our reactants, and they're going to produce a product, and that's essentially what we're going for, that we're going to add these two things together, they're going to react, and we're going to get this. But a big part of equilibrium is that we can actually run this reaction in reverse. We could actually essentially switch things up so that we've got two ammonia. I know, guys, remember it's tough to write like this. And that's going to yield for us our nitrogen plus our hydrogen. In other words, the exact same reaction but flipped, okay, that we change this to become our reactant and that these things become our products, okay? And essentially the heart of equilibrium revolves around this idea that we can reverse not every chemical reaction, but a lot of chemical reactions actually run in both directions. And the degree to which they run in either one of those directions and where the point that they stop at, like how much product, meaning in this case our NH3, do we make and how much reactant is left, that the point at which that those things become stable, that's what we call equilibrium. We'll talk a little bit more about what the definition actually is here in a minute. So again, if we look at this reaction that we used all the time, we used it for a lot of our stoichiometry stuff last year. We use it when we started out balancing reactions. This is because it's a pretty important industrial reaction. The reaction itself carried on at a pretty high temperature. It's called the Haber process because we're using it to produce ammonia, which is an important precursor chemical for us to make a whole bunch of other chemicals. And so if we look at this, what we've got here is we've got, in this case, I've got a couple of molecules of nitrogen. I've got several molecules of hydrogen. And so what we would expect to be produced if we were balancing this out is that we would get 4 moles of ammonia, because remember I started with twice as many of these as I needed, twice as many of these, and so therefore I'm going to get twice as many of these. Now that we know that reactions are reversible, though, what we can say is that what we could have happen is that about half of these ammonia molecules could go away, okay, that we could essentially cross half of them out. These ones down here will cross out, and they could go back to create more nitrogen and hydrogen. Now again, remember the nitrogen and hydrogen we assumed initially was consumed in our production of our stuff here, but then we were in the reaction reverse. And so at the end of this process, we have a situation where we still have nitrogen, we still have hydrogen, and we have ammonia. We have reactants and products all in that same situation. Of course, since this is an important industrial process, what we really want, obviously, is more of the product at the end. So what we'll talk about later in this unit is how do we get this, how do we force this to produce mostly products? We want to get that percent yield that we talked about in Chem 1 as high as possible if we're doing industrial type things. So just another example of what equilibrium is, and you may recall that we talk about this one in class occasionally. If we've got a classroom, and let's say that classroom has 9 students in it, and we've got 1 student outside, if we want to maintain the equilibrium in the classroom, or in other words, we want to maintain the concentration of students in the classroom, if I add another student, then a student has to leave. And we can think about these things as sort of a forward, okay, and a reverse reaction, reverse being that it's going out the other door. And so that could indeed keep happening. And so we could say, let's bring another student in, and to keep the equilibrium, another student has to leave. The concentration of the students is staying the same inside of the box as long as every time a student comes in, another student leaves. And if we think about that in molecular terms, then that's also true, that we're still at equilibrium even if we change the actual, what the molecules, like which molecule it doesn't really matter which molecule it is as long as the concentration of them is the same. And the same thing would go here for a concentration of students. As long as every time I added that student in, a student left, then our concentration stayed the same in here. What that also means is that the rate, okay, and we talked a lot about rate in kinetics, that our forward rate over here, okay, is going to need to equal my reverse rate over here, that the rate at which I'm putting students into the room has to equal the rate that the students are going out of the room for us to maintain equilibrium conditions. Okay, so let's look at this a little bit more with actual molecules. Okay, so again, we're going to look at our nitrogen and hydrogen here. We're talking about the same reaction, okay, N2 plus H2 equals NH3, okay? And so we're going to start out here with normal initial conditions. And what initial conditions would be for us a lot of times is we don't have any products, okay, that we put in our reactants and we're waiting on them to react. So those things are going to react, and as some of them react, we're going to start to get some of our products. Now, ideally, under our old scenario, what's going to happen is that they're all going to react, and we're going to end up with nothing but products left at the end. Okay, but now that we know that reactions are reversible, what we can see happens is that even if everything did go all the way to the end, all the way to the right of the reaction, we would say at one point, then it's entirely possible that some of it goes back. Okay, and so this is going to leave us with a condition at equilibrium where we've got essentially all of our species of chemicals in this container. So I've still got some nitrogen and hydrogen, and I have some of the product. And again, obviously industrially we want to maximize the product, but we have to manipulate the equilibrium conditions so that we can do that, because under normal equilibrium you might still have some of the product, and that depends on the individual reaction. There are reactions that will essentially go pretty much always to 99% product. And then there are others that will not go very far to products at all, that you might get 10% product and 90% reactants. And so a big part of equilibrium chemistry then is how do we manipulate the conditions, okay, what stresses can we put on the system to force it to go in the direction that we want it to go. Okay, so that leads us to then what is the definition of equilibrium. So there are essentially two points here that you can know that you're at equilibrium. The first of them, and we talked about this one earlier, is that equilibrium is the state at which the concentrations of the reactants and the products are constant with time. So that we might initially start out with H2 and N2, but that eventually those will taper off and become constant. And even though we didn't have any ammonia at the beginning, our concentration of it increases, but that it also starts to become constant. And the point at which all of the concentrations become constant, that's equilibrium. Okay, so that's in terms of concentrations. We can also define equilibrium in terms of our rates of our reactions, and what that would mean is that at the beginning, if we think about when we just put the N2 and the H2 in there, when we just put those two things in, obviously we pretty much only have a forward reaction. There's no product to even go in reverse. As we start to generate product, though, we start to get a reverse reaction, and eventually what's going to happen is we're going to reach the point at which these two things are happening at the same rate. And again, think about the kids in the classroom, that as long as every time a student walks in the classroom, one walks out, then the rate is equal, and therefore the classroom is in an equilibrium scenario. Okay, a couple other quick terminology things for when we're talking about these reactions. If we say the reaction lies mostly to the right, that means that we're mostly getting products, and that makes sense. I mean, if you think back to what our reaction actually was, okay, and again, I'm going to try to write on here, so sorry about that, guys. So if we think about what our reaction was, and again, remember we've got to have this double-headed arrow here. I'm sorry, not double-headed. We have to have two arrows, each going different ways. A double-headed arrow is different. Remember, that's resonance. Okay, and that means something entirely different in chemistry. But what this means is that if we say that it lies to the right, it means it lies on this side, what we would traditionally think of as our products. And indeed, the way we wrote this reaction, then that's the product. Okay, and again, how would we know that that happens? Well, there's a bunch of math that goes into it, which is what we're going to spend a lot of this unit talking about. If we say that the equilibrium position lies to the left, then that means that we're favoring the reactant. So if we look back at our reaction from the previous page here, that would mean that I'm getting more of these guys than I am of the product. We could say that that reaction isn't going very well, or that our percent yield isn't very high product-wise, but in equilibrium cases, we would say that the equilibrium lies more to the left than it does to the right, because it's favoring the reactants, what we would typically think of as things on the left-hand side of the reaction. All right, guys, that's just some basics. In our next video, we're going to talk about equilibrium constant, which is where we're going to just sort of touch on and begin to talk about the math that's related to this. And then in the video after that, we'll start to talk about how do we actually manipulate this, how do we work out all of the math required for it, and you'll see perhaps maybe some uses of all those polynomials and quadratic equations that you learned in math class. Thanks, guys.